Hello, and thank you for joining us in this second podcast in our series on Applied Research in Photonics Incorporated, ARP. In our first podcast, we introduced and provided an overview of ARP T-ray technology. Today, we dive into a discussion about specific applications of teraspectra, the ARP T-ray nanometrology tools. My name is John Mahoney, president of C4 Technologies, a sales and consulting company. We support semiconductor and OEM electronics for process and inspection tools. We are joined again by Dr. Anis Rahman, President and Chief Technology Officer of Applied Research in Photonics, Inc. Dr. Rahman is inventor of T-ray-based technologies utilized by ARP in the manufacture of nanotechnology enabling tools. Dr. Rahman, thank you for joining us today.
Good afternoon, John. Thank you for arranging this. Appreciate it.
You're welcome. So, Dr. Rahman, ARP's T-ray technologies have virtually, it appears, unlimited potential in the inspection and analysis of advanced materials and processes across broad scientific and industry applications. Today, however, we are going to focus on an extremely important semiconductor T-ray application, whole wafer profile mapping for die sort and analysis. In fact, you have published a paper in 2023 titled T-ray wavelength decoupled imaging and profile mapping of a whole wafer for die sorting and analysis. Can you summarize what this ARP T-ray application accomplishes and why it is important to semiconductor fabs?
Right. Thank you, John, again. And it's very important question as well as the issue of entire semiconductor industry, which is the yield. If they fabricate a wafer is the basis for all electronics on which die, in other words, chips are made. So these two terms, die and chip. Die is when it's on the wafer, and when it is cut and packaged, then it becomes the chip or device. So a blank wafer is only 100 to 100 bucks, or few $100. But on a 300 millimeter wafer, these days the die size is 3-4 millimeter by 3-4 millimeter, 3 or 4 millimeter, and then they leave some room for cutting it, and then start the next one. And that way, on a 300 millimeter wafer, there can be 10,000 or more die. That number is very important because each die become a chip, and each chip become a device like cell phone or computer CPU or other application specific IC. So the value of a single wafer jumps up tremendously high. And that value is realized only when all the die on a wafer are packaged and used. But what happens is, even though the process has been perfected, but still not all die turns out good on a wafer. Some die are good, some die are not good, even from the same process. So the manufacturers must know which die to package and which one is not good. So the way it is done now, and it's important to understand our value, because how it is being done today. I mean, semiconductor industry is thriving despite all those difficulties. But the way it is done today is they have multi-probe electrical testing station. The wafer is taken there, and the probes come to the selected places on each die and measure the electrical property. And from there, they can determine a good die or a bad die. And but if they have to test each and every die on the wafer, it will take very long time because of the probe technique. Physically, probe has to go and touch the electrodes spot on there. And that's why what industry does is, as a general practice, they have defined a threshold of bad dies on a given wafer from their experience. And if the multiprobe testing with random dies exceeds that threshold, then they would rather start with another wafer than checking each and every die on that wafer because it's above that threshold. And so that said, then even though they are rejecting that whole wafer, there are good dies on that they could package instead of throwing away the whole wafer. So there come the T-ray. What we found is that with T-ray, we came up with a proposal called profile mapping. If we have a known good die, which is the key, then the profile of that known good die against T-ray should match the profile of all good die on that wafer. So if there is a discrepancy between profile of a known good die and another die, then that die is not a good die. And we can, with T-ray, one can do this fairly quickly. In matter of hours, they can scan the entire wafer with all 10,000 or more die on it and sort them. You know, they can easily number in the program. It's nothing has to be done physically on the wafer. That remains untouched. So it's a non-contact method as well, non-destructive, of course. And then one can number 1 to all the 10,000 dies and assign them which one is good and bad. Therefore, on the second step, pick and place machine can go pick the good ones and move on with packaging. So this is basic proposition that we think right now the rejection rate is minimum 30% for established processes. Therefore, their yield can go much higher than 70%.
Okay, excellent. And of course, the prospect of packaging die is a very expensive process for semiconductors. So being able to package only the known good die that have been sorted is very important, saving a lot of money potentially for semiconductor fabs. Thank you. So we have discussed teraspectra, 3D imaging, and spectroscopy. Are both capabilities used in the profile mapping and die sort, or one or the other?
Yeah, and the teraspectra, as you mentioned at the beginning, is a pretty versatile instrument. But fortunately for profile mapping, we do not need everything. All we need is the imaging system. And also the imaging system, although imaging system allows us to image the whole wafer, we may have to do that for 1 or 2, but for profile mapping, it's not even necessary to image the whole wafer because time savings is important here.
Sure.
So in this case, the procedure is that first of all, we identify one known good die, and that may be done by electrical probing, or it has to be the known good die, meaning known good die, right?
Sure.
So, and then we profile that one and save it as the reference, and then keep scanning all the dies and compare with the reference on the fly.
Sure.
So this is much simpler, both in concept as well as in usefulness. I mean, using the machine compared to spectroscopy, imaging, and all of those things.
Okay. And when you say profiling, are we talking about a topographical image, a 3D image? Are we looking at contrast of perhaps different materials? Could you maybe explain profiling just a little bit?
Yeah, it's even simpler, because what is an IC? On the die is the arrangement of material in different ways. In the very simplistic term, right?
Right.
And they have different layers. As you know, the dies are made. One layer pattern it, then another layer pattern it, and so on and so forth. There may be hundreds of layers. So T-ray being able to penetrate, it's a line scan, and along a line scan comes the profile. So profile of one line scan, that gives all the fine details of the material arrangement
Yes.
of that particular die.
Okay.
And that is the key for making it fast, high throughput.
Very good. And certainly the profile mapping, once the bad die are identified, they're simply not put forward towards final packaging. So these T-ray tools, the TerraSpectra for profile mapping, these are currently available from Applied Research and Photonics.
The instrument is available. Mainly, it's an imaging tool, but it's another application of profiling where the whole image acquisition is not necessary.
Okay. Dr. Rahman, you mentioned that recently you attended Semicon West in San Francisco. Did you have any interested parties in, it would seem like the engineers and scientists for the semiconductor fabs would be very interested in this technology to save millions, perhaps, of dollars daily for the semiconductor industry. What was your feedback from the engineers that you perhaps met at Semicon West?
Yeah, there are actually a lot of interest of the technique and the technology. The hard part is the implementation. So we need to be able to find some, early adapters. We need to find some internal champion who we can work with, because the key here is the known good die. Unless we have a really known good die, we cannot implement for actual,
Sure.
packaging. So that is, I mean, I met quite a few distinguished companies. They are scientists and engineers and decision makers, and exchange cards and everything like everybody does. But the whole objective over there was to explain the science, share the science and technology of it, making actual implementation is the one that we actually need to focus on.
Sure. I'm sure that our audience would be very interested in obtaining some more information, and perhaps even the publication that you put out in 2023. Our listeners can obtain that through info@arphotonics.net. And we'll post that that email address so that at the end of the broadcast, so that our listeners and viewers can make a request for more information about the profile mapping and dye sort analysis.
Absolutely.
Dr. Rahman, is there anything else you'd like to add to today's discussion?
Yeah, I think in summary, what we can say that this is a new technique, and as such, the awareness is not there.
Okay.
On the other hand, even the wafer fabricators, fabrication facilities, even they have only one wafer that pays for this machine.
Right. Just saving one wafer would be a positive return on investment for a semiconductor fab.
That's exactly right. And see, so they have a tremendous opportunity to improve their yield, which translates into their revenue.
Well, let's hope for applied research and photonics that this podcast reaches some decision makers in the semiconductor fab world and are open to a discussion about doing an evaluation on their fully populated wafer prior to packaging. And I'm sure that you and ARP are open to having those engineers visit your facility and evaluate their wafers in your laboratory.
Absolutely. Sure.
Well, fantastic. Well, Dr. Rahman, as always, it's a pleasure talking to you. And we'll schedule another podcast in the near future. And for now, thank you very much and have a great day.
Thank you, John.
Bye for now.